So let's begin today by talking about something known as the Taylor series expansion. So the Taylor series expansion is actually a generalization of the power series representation. So let's go ahead and write out the definition of a power series. F of x equals the sum from n equals 0 to infinity of some coefficient c sub n times x minus a to the n. So that x minus a to the n is the power, and c sub n is the coefficient of our power series. And so we can write that more explicitly as c naught plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus c4 x minus a to the fourth plus ... all the way up to infinity. So a is just some constant value along the x dimension. So if x equals a, all of our terms with x minus a are going to go to 0, and we can evaluate the function f of x at a such that we've defined c naught. Okay, so if we want to use this expansion, we're going to need to know the definitions of the coefficients c sub n, and we can do this by taking the derivative of f of x and evaluating it at a to solve for the coefficients. So if we do that, we're going to have f prime of x equal to d dx f of x, depending on the notation you prefer, which is equal to c1 plus 2c2 x minus a plus 3c3 x minus a squared plus 4c4 times some value ... And so all those terms with x minus a are going to go to 0 because we're evaluating this derivative at a. So that means that we're going to have f prime of a equal to c1. So we've got one coefficient here, we've got another coefficient here, and we can continue this process to find as many coefficients as we want. So we'll do that up until about the third or the fourth derivative to get a pattern, and then go ahead and define the definition of the c sub n as a sum itself. So for the f double prime, plus 12 c4 x minus a squared plus the higher order terms, and that means that c2 equals the second derivative of f evaluated at a over 2. So that's our third term there. And then we're going to go ahead and take the third derivative And we can go ahead and isolate the coefficient C3 and find that it's equal to the third derivative of f, evaluated at a over 6. So that's going to go ahead and be our fourth coefficient. And then our fifth coefficient is going to be the fourth derivative of x equals d f of x dx to the fourth equals 24 c4 plus some term that involves x minus a. So c4 is going to equal fourth derivative at a over 24. So we've found 5 coefficients in the power series, and if we look at the pattern, the nth coefficient is the nth derivative of f at a over n factorial. So let's go ahead and generalize this as well, a definition. We'll say c sub n equals f to the n at a over n factorial. Okay, so looking at this definition, if we plug it back into the power series representation of a function, we're going to have the definition of a Taylor series. So let's go ahead and do that. F of x equals the sum from n equals 0 to infinity, and then it used to be c sub n. We're going to rewrite it as f of n evaluated at a over n factorial. So that f to the n of a is the nth derivative of f evaluated at a over n factorial times the quantity x minus a to the n. Okay, and that's going to be our definition of a Taylor series. Okay, so a lot of students have questions about where the relationship between the Taylor series and the Maclaurin series comes into play. So in order to illustrate that relationship, let's write the Taylor series out explicitly. And so that's going to look something like f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f third derivative of f evaluated at a over 3 factorial times x minus a cubed plus the higher order terms. And what that tells us is if we evaluate the Taylor series at x equals a, we can rewrite the summation in a different manner. And so what that gives us is f of x equals the sum from n equals 0 to infinity, the nth derivative of n evaluated at 0 over n factorial times x to the n. Okay, So the only difference between the Taylor series and the Maclaurin series is that the x equals a. And when x equals a, it becomes 0. And so that's our Maclaurin series. And with numerical methods, we need to come up with a way to express the error of the Taylor series expansion, because it's not the exact expression we're looking for, f of x, because there's no way to discretize infinity. This sum in the Taylor series represents the function as n approaches infinity. However, in real life, we have to use a discrete value of n. So there's going to be some round-off error between the Taylor series and the exact value. So in order to describe that error, we need to define something called the nth degree Taylor polynomial. So the nth degree Taylor polynomial of f of x looks like this. T sub n of x equals the sum from I equals 0 to n f of I, the ith derivative of f at a over I factorial times x minus a to the I. And what that does is it converts the Taylor series expansion from an infinite sum to a discrete valued sum, where we sum until n instead of infinity. So let's use that definition to talk about round-off error. So the round-off error is going to be r sub n equals the exact expression f of x that we're trying to approximate minus t sub n of x. Okay. So our error is equal to the exact minus the numerical approximation, and the numerical approximation in this case is the nth degree Taylor polynomial. And we're going to go ahead and give an example of this. So our example is going to be a Maclaurin series for f of x equals cosine x. Since we have a Maclaurin series, we'll go ahead and say that f of x equals the sum from n equals 0 to infinity, the nth derivative of n, the nth derivative of f, at 0 over n factorial times x to the n. Okay? And a great way to get this problem started is to just write out a few terms. For n equals 0, we have f at 0. For n equals 1, we have f prime, the derivative, times x. And then for the next term, we have f double prime at 0 times x squared over 2 factorial. And then for the following term, we have the third derivative times x cubed over 3 factorial. And then of course we have the higher terms approaching n equals infinity. So what we need to do is we need to take that cosine of x and plug it into this equation right here, and that's going to give us something like cosine and then we're going to have minus sine then we're going to have minus cosine then we're going to have our sine plus our higher order terms. And what that does is it gives us an alternating series, which looks like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, etc., etc. Okay, and so with this information we can go ahead and define the Maclaurin series for f of x equals cos x, such that f of x equals the sum n equals 0 to infinity minus 1 to the n x to the 2n over 2n factorial.
So here I think it's useful to go ahead and describe how to write a subroutine in VBA for a Taylor series or Maclaurin series expansion. So we can do that by going to the Developer tab and clicking Visual Basic, and from there we can go to Insert Module, and it's going to give us our workspace environment. So as usual, we're going to open up by saying Option, Explicit. Then we're going to say Sub, and we can name our subroutine whatever we want. In this case, we'll call it something like Taylor. And that's going to open and close our subroutine. So using this tab key, we can go back and forth, which is good practice for cleanliness, and we can say apostrophe and comment or annotate what's going on in the code. And for example, opening up by declaring the variables. So we're going to have dim I, n as integer, and we're going to have dim x, Taylor, and factorial as double precision, and we're going to dim exact as double precision as well. So that means that our I and our n, our integer values, our x, Taylor, and factorial variables are double precision, and our exact is double precision as well. And we're also going to evaluate the Taylor series at some point along the x-axis. So we're going to choose a point. We're going to say that x equals pi, for example. So we're going to say x equals 4 times the arctangent of 1, because 4 times the pi over 4 equals pi. And we're going to choose some number of terms in the Taylor series expansion, and we can say n equals 100, for example. The greater number of terms, the more accurate your numerical solution is going to be in this case, and we'll go ahead and talk more about that later. And then our exact solution is going to be cosine of x in this example. Okay, and we want to go ahead and initialize our variables for the series. This is very important. So we're going to initialize the factorial and the series. How are we going to do that? We're going to say that factorial is equal to 1. Why? Because 0 factorial equals 1. And we're going to say that the initial value of the Taylor series is equal to 0. Okay? And then at each new iteration, we are going to compute the factorial and add a new term to the Taylor series expansion. Okay? And our next step is to go ahead and make a for loop for our I equals 1 to n, and tab factorial equals factorial times 2 times I. And this 2 is coming from the fact that we had 2n factorial in the denominator. If we have just n factorial, that's going to become a 1. And likewise, we're going to do that for the Taylor series expansion. We're going to say Taylor plus, and then we had that x to the 2n. In this case, our indice is I, so we're going to say x to the 2 times I times minus 1 to the I divided by our factorial. Okay, that closes out our for loop. And we want to use something called the visual basic carriage return line feed. That's just a fancy way of outputting the data into a message box, or the result into a message box that's nice and clean. And we can furthermore say create a message box solution of the Taylor series result. How are we going to do that? We're going to use MSG, not the Chinese food ingredient, but the command MSG box. And then we're going to use quotes and say the value of the Taylor series is, end quote, ampersand, and then we're going to use that Visual Basic carriage return line feed command ampersand, and then we're going to output our Taylor series, comma, comma, and then this is going to be our numerical solution, okay, end quotes. Furthermore, we are going to create a message box for the error of the Taylor series expansion. Okay, and so we're going to say once again MSG box the error of the Taylor series is, end quotes, ampersand, and we're going to go ahead and use that command as before. And we're going to say this time we're going to take the absolute value of the exact solution, which is the cosine of x, and we're going to take that minus the Taylor result, comma, comma, and this is going to be our error. Okay. So let's go ahead and run it by either clicking the triangle, the green triangle, or pressing F5. And so here we have a box that says the numerical solution, and the value of the Taylor series is minus 0.99, etc. We can click OK, and the error of the Taylor series is 7 times 10 to the minus 3, which isn't bad either. Okay, so that's a pretty nice subroutine. I wanted to point out that if we change this number of terms here to example, I don't know, 10, we have 10 terms in our Taylor series expansion, and then we run it, you know, our approximation is really bad. We've got minus 0.24, and we know that the cosine of pi is equal to minus 1, so this isn't even close. Okay, and the error is just huge. It's 0.75. So if we add more terms, say 15 terms, we get that minus 1 back. So, and then the error becomes much better than it was for 10 terms, and then once we use something like 50 terms, the error gets even smaller, and we're converging to the best solution possible from the Taylor series. So basically what this demonstrates is that as n approaches infinity, our Taylor series is more and more accurate, just like we would expect. Okay, so I hope that helps explain to you what's going on with Visual Basic, subroutines, and for loops, and Taylor series and series in general. Okay, thank you. Bye.